want extra questions to work on for somebody emailed me about getting some extra questions. So extra questions, you can use that chapter, the chapter 7 for extra questions based on chapters 1 to 6, right? So chapter 6, we'll start with chapter 6. They're called two-way tables. They're also formally called contingency tables. And this is a way for us to study the relationship between two categorical variables. Okay, so we're talking about categorical data here in this chapter. And we'll look at their marginal distributions, their conditional distributions, and also there's this strange paradox that we call Simpson's paradox. It's quite strange. So you'll see what that is as well. So what is a two-way table or a contingency table? It's a table where we organize the data in such a way where we can get the counts of each categorical variable. And there's the row, one categorical variable is the row variable, and the other categorical variable is the columns. And they're arranged that way so that when you cross tabulate, you can get a count from each, right? A count that would cross both. So just like here, this is the case study. It was a roadside survey, and it was asking random participants who wanted to participate. They were just pulled over the side of the road in state of Oklahoma. Were you drinking within the last 2 hours? And it was volunteer for them to answer yes or no. And then you can see here, there's many more males than females, which is just the natural phenomena with driving. There's usually more males on the road than females. But what we do, as we discussed last time, is we use percents. So the percents is how we compare these. How can we compare if we use percentages instead of raw counts, right? Because the number of males who said yes is 77, and the number of females that said yes is only 16. But if you divide by their totals, we get percentages. So 77 divided by 481 and 16 divided by 138. That's how we get those percentages. And we'll work through those in the next few slides, those percentages. So what are the variables in this two-way table? What are the two categorical variables? One is yes, no. It's the answer to the question. So it's a yes or no. And they don't have numbers, right? Yes or no. It's yes or no. So it's categorical. It's people either answered yes or they answered no. And then there's the gender where they answered male or they answered female. That was the result of the study. So that was the data. If there was other, male, female, other, there would be 3. And each of those is called a level. So the gender has, in this case, 2 levels, whereas the drank alcohol in the last 2 hours also has 2 levels. But there could have been 3. It could have been yes, no, maybe against male, female, other. It could have been 3 levels by 3 levels. But because we have 2 and 2, this is 2 levels for each categorical variable. But they can be larger. So if we look at the marginal distributions, that's just looking at one variable at a time and getting their raw counts. Okay. And I'm just going to highlight here, percents are often more informative than counts, especially when one is comparing the groups of different sizes. That's why I use this example. It really shows the differences in sizes. So it's crucial that percents are used. And so we're going to examine a marginal distribution. We'll look at each one at a time. And then we can look at the row variable, and then that's just that distribution. And then we'll look at the column variable. In this case, the row variable is gender, and the column variable is the answer to the question, yes, no. The survey question, you can call it the survey question. So here they are, just looking at the marginal distribution for just gender. You can see in the bar chart, there are a lot more males than females in the study. And visually you can see that. And same with the answer to the survey question, there were a lot more no's than yeses. So you could see a lot more males and a lot more no's. So this is when we study each categorical variable separately, each at a time. When we want to study them together, we put them into the two-way table and compare the percents. So if we are just looking at one variable at a time, it makes sense that it's going to tell us nothing about the other variable. So if we're just looking at gender, we know nothing about the survey question. Likewise, if we're just looking at the survey question, right? If we're just looking at the plot on the right, it tells us nothing about the gender question. So marginal distributions literally are just separating those two variables and studying them one at a time. The conditional distribution of a variable, though, describes the values of the variable among the individuals who have a given value of the other variable. So that's the conditional distribution. So here's the questions here. What percentage of males responded yes? And so these are the type of questions. Each one of these could be a short answer question, or this could be turned into a multiple choice question. So what percentage of males responded yes? So what we do here is we grab 77, right? We look at the cross tabulation of yes, right? And males. And we get 77 for that. And we want the percentage of males. So we want to divide that by 481. And we get 0.16 or 16%. I'll just put the percent in brackets. Okay, so what we're doing is we're taking the males and just seeing how many said yes and dividing by their total. Their total is there. The last totals. Sometimes these two-way tables do not give the totals. You have to just add them up, like add the row total and then add the columns, and then you have the totals. But sometimes they're given in the question, sometimes not. Okay, so the next question is, what percentage of males responded no? So this time we would take this value, right? Males, no. You find the cross tabulation there, and it's 404, 404 males. And we divide that by 481. And we can get the percentage that said no. And that comes to 84%. Okay. So far, so good. We can find those values pretty straightforward. What percentage of females responded yes? So we then go to the female row variable, yes and yes. So we get 16 and divide by the total number of females, which is 138. And we do 116. You can, if you have your calculator, you should have your calculator, and just try those quickly. And I'll get mine ready too, just to make sure for accuracy. And that ends up being 11.6%. Yep. We do lots of calculations in this course. It's always good to have the calculator ready. And so the next question, what percentage of females responded no? So we are still in the row of females, but this time no would be 122. And the total number of females in the survey was 138, which gives 0.884 or 88.4%. So by the way, this number here, can anyone tell me what that number represents? 619. Yes. Yeah, it's the total number of participants. The total number of participants in the survey combined, 619. So there was 481 males, 138 females, grand total 619. And it should add up to the same number as the number that said yes, which is 93. The total number that said no was 526. Those should also add up to 619. Okay, so we call it the grand total, right? Now so far it's been pretty straightforward. Now the questions you have to think about, which variable are they wanting out of this and which one should I divide by? So of those who answered yes, what percentage were male? So it's different. This is different than what percentage of males responded yes, right? The wording. So this chapter is all about the wording of the question. It changes the answer. So of those who answered yes, what percentage were male? What would I put here? Exactly, 77, we know said yes, but we want, of those who answered yes, we want to divide by 93, right? And we get 0.828 or 82.8%. If you have room on your sheet, you can put in the 82.8%. All right, so let's try the next one. Of those who answered yes, what percentage were female? So it's similar, but it's going to be of the females. Yes. Exactly. 16 is in the numerator. 93, the denominator. And so we have this time, you can put that into the calculator straightforward, and we get the proportion, which is 0.172. So I'm not giving the percentage, I'm giving the proportion. If you leave it just like that, it's a proportion. To convert it into the percentage, it would be now 17.2%, right? So one is a proportion. I'm running out of space here, but the ones above it that were in brackets, those are the percentages. So one's proportion, the ones in the brackets are percentage. Should, yeah. And if it's multiple choice, they will be provided in percentage. Yep. Sometimes, and it's a mix. You'll see with the questions, you'll see sometimes it's proportion. What's the proportion? What's the percentage? You'll see there's a difference, right? Okay. Yes. For the multiple choice, it will be provided for you. You'll see what level of precision they're looking for. But with the show your work, for these type of questions, it's best to do up to 3. Yeah. And even there was some questions, remember in chapter 3, and even chapter 2, when we did the standard deviation, it's always good to keep as many decimals as possible until the final answer. And if you round to, and the question should specify round to 3 decimal places or round to 2, and you just follow the instructions from there. But don't round as you go, round only at the end. Yeah. Yeah. And here it's just, there's just one calculations. So, but those are good questions, all right? Of those who answered no, what percentage were male? So of those participants who answered no, you want this column, and then you want to go what percentage were male. So how would we do this one? Yes. Right, 404 divided by 520, 526. Yeah, so good. 404 divide by 526. And if we work that out, I've worked that out, and please check, I get 0.768. Yep. Yeah, because if you actually put that in the calculator, you get 0.768060836. Now, you would never report that in a report to a manager or a boss, right? That's just too many decimals. So usually it depends what the problem is, but if you're just looking at this, 76.8% would be good, right? It's enough. 3 decimal places. And finally, the last question, of those who answered no, same column variable, right? What percentage were female? Yes. Perfect. 122. Divide by 526. And that is going to give us 0.232 to my calculation, 0.232. Anybody disagree with that? All looks good? Okay. Yeah, so that's how we get those conditional distributions. Again, the marginal distributions are the values that are in the margins. We call it the margins because it's on the outside. This is the margins. Those are the marginal distributions, all the totals. It's all the totals. But the conditional distributions are the ones where you have a yes or no cross-tabulated with a gender. Okay. All right. Any questions? It's not too bad. It's a nice, most students don't find this too bad. It's actually interesting because how do you study color and, and, things that don't have numbers? Well, we turn them into counts, right? So they don't, yes and no doesn't have a number. Male, female doesn't have a number, but we turn them into counts and then we compare them using these percentages or proportions. And it helps decide if there is a difference or not between them. There's the conditional distributions there. So if we have, I did color for these. So I teach a data visualization course. So I like to play around with the colors. So here you can see instantly the female and versus male. So many more said no versus yes. Okay. And then this is if we switch. And we have the percentage instead. That's all that is changing. So I'll just show you on this slide here, we are looking at the counts, the raw counts, and here we're looking at the percentage. And it really changes, right? I wish I could do a split screen here, but if you probably can see them both if it's on in front of you, you can see it looks very different, right? The no's and the yeses looks like way higher for the male, but when you look at the percentage, it's not much different, right? It's closer in the percentages. And then this is just another way to look at it too. We call it a stacked bar chart. And you can see that the differences are very small when you look at it that way. And it was enough for the young male who was fighting this in court, saying it wasn't fair to not be able to purchase alcohol. Only females could purchase alcohol within a time period each day. And then he fought it, used this data. It went to the US Supreme Court, Supreme Court of the United States, and he ended up winning because of this. So it was enough to support the case. This has also been studied lots. The famous Titanic, everyone's heard of the Titanic, the sinking. I don't think there's too many people in the world that haven't heard of this. In 1912, the large ship wasn't supposed to sink, but it did off the coast of Canada. 1,490 of the 2,201 passengers perished. And then I have put together a two-way table that shows the counts of the survivors and the victims. I didn't include the first and second class passengers because most of them survived. But unfortunately, it was the crew and the third class passengers that most of them did not survive. So we're just going to compare them, the crew of the ship and the third class passengers. Yeah, so just for simplicity, we're just going to have those. So here is what it looks like. We have third class passengers, and you can see the survival rate was 25.2%. So how did I get that? It's in blue. How did I get that survival rate? So we have here that so just to orient ourselves, we have two categorical variables. The one is whether they survived or died. So that's survivorship, survived or died, yes or no. And the other categorical variable is the row variable, which is the passenger. Okay, so it's either third class or they were crew. So how do I get this 25 for here? So you can see more third class passengers survived than, say, the crew. How did I get those numbers? Anyone? Yeah. Yeah, so if I take the survived, so this value here, 178, divide by 706, should give it to me. Yeah. Right? That one? And this one here should be 212. That's the number that survived, divide by 885. So what this tells us is there was 885 crew members, and there were 706 third class. So there was quite a lot more crew than third class, but yet the survival rate for the third class was a little bit higher, 25.2 versus 23.95. Right? They still study all this data to this day about the surviving and how much they paid for a ticket and that, and it's used a lot for demonstration of categorical data. So it looks like the third class passengers had a better chance of surviving than the people in the crew. And then I have ... or did they? So if we look here and I stratify the data and make two more tables, but this time separate the males and the females. So the male third class and crew, and the females third class and crew, you can see instead of third class having a higher survival rate, it's the crew in both times. So contrary to the previous slide, the crew had a better chance of surviving than third class passengers for both men and women. How did this happen? How did this happen on the Titanic? Anyone? Yeah. Yep. Yeah, women and children. Yeah, women and children were first, right? And that was a large reason why this is happening. This whole change in survivorship. So we had the crew, right? There was the third class had a higher survival rate, but then when you stratify by males and females, you can see that it's the crew instead of third class. So this is called Simpson's paradox. So it's a paradox. Soon as you add in a variable, lurking variable, and you add that into the study, in this case, gender, then we see a reversal in the percentages, right? So everyone see that? We have third class with a higher survivor rate, but when we take into consideration gender, we have the crew with a higher survivor rate. So there's a couple of things happening here, not just women and children first. They did that, of course, but also the crew, there were more men, crew, right? So that is why it changes too. There was more males than females. So that's what changes it. So adding that variable, right? At first glance, it looks like the third class had a higher survival rate. However, we take gender into consideration. The original impression is reversed. It's a reversal. So you think it's going to be this, but then you add another variable and it reverses. Why? Just as we discussed. So there was more men in the crew group than in the third class group. And the reverse is true for women, more women in the third class group than in the crew. And then men were less likely to survive than women, and the crew was mostly males. That gave the impression that the crew had a worse survival rate, right? This phenomena is called Simpson's paradox. It's really useful. This is it comes up quite a bit in the world of statistics. Yes? No, because what you would report is, but however, when we take into consideration the gender, then no, they didn't. So it's correct just on its own without thinking about the male and female phenomena. It's correct without that variable. With the variable, then it reverses. Yep. Yeah, because nothing here is incorrect in the math. The math it is what it is, right? It is what it is. It does, the third class absolutely had a higher survival rate. If you don't look at the gender variable, absolutely. You bring in you stratify and make two more tables, you go, wait a minute, we have a reversal here happening. Okay. And this happens in all kinds of different data. It's the lurking variable. It exists. A lurking variable may exist. So you may think it's one way, and then if you're clever enough and you think, hey, why don't we consider this variable, then we might see a reversal. And this happened actually at the University of Berkeley, where they said, hey, how come they're admitting way more males, than females? Why is the university admitting all these males and then females? But then when they looked at each department, faculty / department separately, they seen there was more females and it was more balanced, even except for engineering, that was the only one that was different. There was still more males in the engineering. So it was like, no, we're not really accepting more males. It just looks like that when you just look at males and females. But when you look at the departments, each faculty, the area of study, then it was a reversal. And that was a Simpson's paradox. If you look up Simpson's paradox, you'll see that example because that one comes up a lot. So what happens is the lurking variable creates these subgroups, and failure to take them into consideration can lead to misleading conclusions, right? Because you may think that there's something not fair, right? It might not be fair, but maybe it is fair. If you take the lurking variable, variables not already in the study, you take them into consideration, then you can have more trustworthy conclusions. So I guess going back to your question about the third class, it's sort of a it's not wrong in the math, but it's sort of misleading because when you take the variable gender into consideration, then it's more trustworthy, not misleading. So an association that holds for all or of several groups can reverse direction when the data are combined to form a single group. The reversal is called the Simpson's paradox. Here's another example. And I've seen this example used a lot with like this or which hospitals, but this one here is looking at the counts of survivorship after an accident and whether you went to the hospital by helicopter or by road. Right? So you can see here that by road, 76%, right? 24% died, 32. So you can see then survived 76%. So by road, a higher percent of those transported by helicopter died. So you'd go, okay, I don't want a helicopter. I would want to go by road, right? Does this mean that this is more costly mode of transportation isn't really helping? Should they still just keep it by road, or is helicopter useful in these emergency situations? So if we take, though, into consideration the lurking variable serious of the accident, or whether it's serious or less serious, when you take that into consideration, you can see a reversal happening here. The percent change, survived for helicopter is now higher than on the road, and for the serious accidents, and for the less serious accidents, it is also higher. So when you take into consideration the severity of the accident, that's the lurking variable here. You can see that it's not higher survivorship for road, it's higher for helicopter. Okay. So it's the Simpson's paradox. It's kind of strange. You just have this complete reversal. And this would be more, it's more trustworthy. It's the other one when you just look at the raw counts and you don't consider the type of accident, whether it's serious or not. It's misleading if you just report this and not consider the other. Okay. Right, so this is summarizing that, right? So we have serious and less serious accidents. Helicopter evacuations had a higher survival rate within both types, serious and not serious. So this is just recapturing that. This is not evidence of the inefficiency of helicopter evacuation or efficacy of helicopter evacuation, right? So when we put in the type of accident, when it's ignored, or when the lurking variable is ignored, the data seems to suggest that road evacuations are safer than helicopter evacuations. However, when this type of accident is considered, we have the Simpson's paradox. Okay, it's kind of neat. So there's the Titanic, this example with the helicopter versus road evacuation, and the one with Berkeley University. So here's one for like psychology, what percentage of, so we're looking at a survey questions about one's happiness and health. Using the results of the survey, answer the following questions. So part A, what percentage of those who were in fair health were pretty happy? So we're looking and trying to compare here health and happiness. Are healthier people happier? And you can do that by having some data, getting the survey, right? And checking it out. So what should we do? So you're given this table, and for health status, we have poor, fair, good, and excellent. So 4 levels, right? For the happiness, not too happy, pretty happy, and very happy. So 3 levels for happiness. So we have 2 categorical variables: happiness, level of happiness, if you will, and health status. So health status has 4 levels. Level of happiness has 3 levels. How would we answer the question? Anyone want to take a go at it? Yes, go for it.
Their health and pretty happy,
Yep.
and then
In the fair, exactly. So that's exactly it. So you might be going, do I use a row total or do I use the column total? And because of the wording of the question, that's how you will get to that answer. So what percentage of those who were fair, so that's what we want in the denominator. Of those who were in fair health, we're pretty happy. So I'm just going to grab my. So the answer will be 21, this number, divide by the column total, not the 67, but the 47, because we want of those who were in fair. So when you think of it, you go, okay, I want of those who were fair health. And then you can go from there and go, okay, pretty happy is 21, divide by 47 equals 0.447 and 44.7%. Sound good? Anyone disagree? So it's the wording of the question. You want to be very careful. What about part B? Of those who responded not too happy, what percentage were also in poor health? Bless you. So of those who responded not too happy, so that's this, right? So what would I put in the numerator? Numerator 6, yes, 6. Denominator 30, exactly. This is what we want, and we get 0.20 or 20%. It's out of 31? I get 30? No? What's out of 31? It's 30, right? 30. Unless we have a different number. It's 30, right? Okay, so that's a good question because that comes back. Do I use 30 or do I use this number? But it's not this 30 because of the wording. So it's of those who responded not too happy. You look at that row. So of those who responded not too happy, that's what you want to look at. And then you go, we're poor. health status. So 6 divided by 30. Had it said of those who had poor health, what percentage were not too happy, then it would be 6 divided by 31. Okay, so it's the wording, yeah. Yep. And what percentage of respondents, last question, what percentage of respondents said they were in excellent health and very happy? So what percentage of respondents? So how do we do this one? Let me get rid of all this so it's not all, it's a new question. So clear the slate. So what we're looking for, what percentage of respondents said they were in excellent health and very happy? What would I put in the numerator? So if I did 73, that would be including the not too happy. So what did they say? Excellent health. So excellent health, this would be 73, right? Yeah, so who said 73? It's good. I think 73 is good. And what about what else? I'm very happy, right? Health. I'm very happy. Actually, yeah, so how would we do that? So it's going to be, we want a cross tabulation. So for this question, it's going to be this, right? Excellent and very happy. And what's the denominator then? 73, 103? Yes, that's it. 36 divided by 200, because it says what percentage of the respondents? We know that there were 200 total respondents in the survey right here. So what percentage of the respondents? That would be the denominator. Good. 36 divided by 200. We made it. And let me just go to the end here. All right. Anybody disagree? 70%? I don't get that. I get different. I get different. This is a different question. 18, right? Thank you.